Good morning. This is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain the Couette flow between moving parallel plates. So this is the schematic of the problem here. So you have two parallel plates. One is here in the bottom, which is stationary, and one is on top, which is moving at some velocity u max, and the distance between the plate is 2h. So the origin of the coordinate is being chosen at the between the center of the two plates gap. So here, so y coordinate is in the perpendicular directions of the plate, x is the direction of the flow, and z is in the direction of the plate width actually. So the boundary condition for this case at y equal to minus h, here the lower side, u equal to u0, the no slip condition because this plate is stationary. At y equal to h on top plate, the velocity u equal to u0 or the u max. It is again the no slip boundary conditions. And other conditions here we have the steady state flow, incompressible fluid, Newtonian fluid also. So these are the constraints. Fully doubled up flow. So if we will put all those constraints on x momentum balance, so this is the x momentum balance. So first is steady state, this term is getting 0. Fully doubled flow in directions x, this term is getting 0. Totally one-dimensional flow, so totally in one-dimensional flow only in x coordinate, so your v is equal to 0. W is also equal to 0. Now this term rho gx, we are not applying any g component in this direction because gx in vertically downwards. So gx equal to 0. Del p upon del x is term is we are considering here in this case the applied pressure gradient. Del u upon del x equal to 0 based on fully doubled flow in direction x. So the velocity should not change in x directions. Now these two magnitude, the del u upon del y and del u upon del z. So del u upon del y always significantly higher than del u upon del z because the width of the plate is much more larger than the space between the two plates. Therefore this term is getting cancelled. So our resultant equations is 0 equal to minus del p upon del x plus mu del square u upon del y square. So this del would be converted to total derivative because y is only variable here now. Now this is del p upon del x applied pressure gradient would be calculated by this way. So p1 minus p2 upon 0 to L minus delta p upon L. So from here this is the expression of del p upon del x. So del p upon del x would be equal to minus delta p by L. So del square u upon del y square equal to minus mu delta p by L. And for that we can write here, we can integrate this. First integration would be this du upon dy equal to delta p by mu L y plus c1 u equal to minus delta p 2 mu L y square plus c1 y plus c2. So two unknowns, two boundary conditions. So first boundary conditions at y equal to 0, u equal to 0. So if we substitute here that that y equal to minus h actually. So if it is y equal to minus h, u equal to 0. So this is here 0 equal to this one. Second condition at y equal to h, u equal to u naught, that top plate is this one. We can if we will add these two, we will get the constant of C2. So adding these two equations, we will got C2 equal to U naught by 2 plus delta P H square upon 2 mu L. Now once we have C2, we can substitute the value of C2 in equation 3 and we will get the expression for C1. So C1 is U naught upon 2H. Now we can substitute back both the constant in equation 2. So we will get U equal to minus delta P upon 2 mu L Y square plus mu naught upon 2H Y plus U naught by 2 plus delta P H square by 2 mu L. And if we'll take simplified form of that, so U equal to delta P H square 2 mu L 1 minus Y square upon H square plus U naught by 2 1 plus Y upon H. Now from equation 1, if we say that this is integration for that, so we have the expression for shear stress tau yx upon mu delta P upon mu L y plus mu naught upon 2. So this is our shear stress profile. So we get tau yx equal to mu U naught upon 2H minus delta P by L into Y. So this is the profile just to calculate shear stress profile. Now volumetric flow rate can be calculated by V dot dA and integrated over the entire cross section area. So area is minus S to S 0 to W U into dA. So we have the expression of U. So this whole is the expression of U. dA is d by into so dj. So this is actually you can integrate this term. So W integration would be easy because Z is width is constant and width moreover is not function of the integration function. So W is multiplied everywhere here. Then this term would be, each of them would be integrated from minus S to H. So we can make it twice. So if we will integrate that from here and then arrange it, finally we will get one expression, this one, Q naught equal to U naught WH plus 2 by 3 delta P H cube upon mu L into W. So from here Q naught upon W we can get U naught H plus 2 by 3 delta P H cube upon mu L. From here we will get the average velocity. Average velocity is Q by A. So we already have width, we can multiply by 2H here. So we will get the average velocity. So is U naught by 2 plus 1 by 3 delta P H square by mu L. So this is the average velocity. So this is all about your Couette flow between parallel plates where upper plate is moving with some constant velocity. Thank you.